Really, what I want to focus on here is we're going to talk about even and odd degrees and what the graphs look like, right? So at this point, all of you should be pretty comfortable with this information, right? So first, just to review, odd degree polynomials have opposite end behavior, right? One side's going up, one side's going down, right? Just doesn't matter, it can switch, but they're in opposites. Even degrees, the end behavior is the same, right? Both ends of the curve are going in the exact same direction, right? Here, this graph, and then this graph over here. Both ends are going in the opposite direction, but the odd degrees are going in opposite directions, even degrees are going in the same directions. And then we talked about like what does a positive leading coefficient versus a negative leading coefficient do, and with the even degree polynomials, a lot of people are just really comfortable just saying it flips it over, right? Which is true, right? That's the easiest visual you can make sense of. But really, it's about the right end behavior, right? If the leading coefficient is positive, the right end behavior is going to make the graph go up towards positive infinity. So we have a positive for this one. Right end behavior is going up for this one, so it's positive. Right end behavior here is going down, so it's negative, and so on. So we know that already, just talking about it. And then lastly, I want to talk about so when I say zeros, if I accidentally say roots, I'm talking about zeros right now. We're going to talk about zeros and x-intercepts, right? So I want to focus on odd degrees right now. So we have first degree, third degree, fifth degree, right? So here you can see it has 1 0, which matches the degree. It's a first degree polynomial. Over here, you can count your 3 zeros. 1, 2, 3, it's a degree 3. Fifth degree, right here, I'm counting 1, 2, 3, 4 x-intercepts, but there's 5 zeros, right? Which one, what's going on? I can only see 4 of them. Where's the fifth? I can only see 4 zeros on this degree 5. Where's the fifth? Ryan?
The second term to the left.
The multiplicity right here, right? Yeah, that counts as 2, right? So there's 5 right there, okay? Now, I have a question. Let's go to the degree 2 for a second, right? Degree 2, you can see your 2 zeros, the green points, right? Okay, what happens if the graph is up, above the x-axis? How many zeros does that have? Huh?
2.
I don't know. We have a disagreement here. Anusha? It has 2 zeros regardless, right? And you're calling them complex, right? Because they're not actually crossing the x-axis, and you're absolutely right. So no matter what, the degree is going to dictate the number of zeros you have, right? But because this red graph doesn't hit the x-axis, it doesn't have real zeros. It has complex zeros. And we kind of talked about that at one point, but we're just kind of reviewing it, right? So use that concept and now focus on the odds, okay? Is it possible for an odd degree polynomial to have 0 real roots, or to have 0 zeros? 0 x-intercepts. Is it possible for an odd to have 0 x-intercepts? David?
No.
Why?
Because they're going in the opposite direction, so one of them's bound to hit the x-axis.
Right? No matter what, odd degrees are going in opposite directions, no matter what. So they must hit the x-axis at some point somewhere, right? So odd, right? Here you can see your 3, but if I shifted this, let's not do it with that one. I'll have another one I can show you, I think. Yeah, I'll show you with another one. But no matter what, right, it has to cross the x-axis. You guys understand that concept? Okay. So even degrees, can all even degrees have 0 x-intercepts? Think about the end behavior of an even, just like this one, right? This one has 0 x-intercepts, right? Can all even degree polynomials have that same behavior, where they have 0 x-intercepts? Yeah, right? If I took this graph right here, and I shifted it up, it's not going to hit the x-axis. It'll have 0 real x-intercepts. That makes sense, everybody? Okay. So it's kind of like conceptual, and that's really what we're looking at right now. So here's an example, and we talked about this before, right? This is a degree 6 polynomial. It has 2 real zeros right there, right? But it's a degree 6, which means it has to have, there's 4 other zeros it has to have, right? And those 2 zeros are, there's no multiplicity there, so that means that this must have 4 complex zeros, right? I can't point to them. I can't show you on the graph where they are, because the graph is made up of real numbers no matter what, so I can't say this is where the complex number is. But I can tell you, and we talked about this before, if the curve turns and switches its concavity twice, right? So here you can count the 2 turns, 1 turn and then 2 turns, right? If it turns twice and does not cross the x-axis in that process, that's an indication that there will be complex zeros as part of this function, okay? So you can say that this behavior right here is the behavior that indicates that we'll have complex zeros, but I cannot say that this is where they are, right? Same thing here, right? It turns twice without crossing the x-axis. There's another pair of complex zeros that will exist. They're just not necessarily located there, all right? So here's a degree 3, right? Whoops. Just focus on this right now, right? So that has 1 x-intercept, like we said, it's an odd degree function, which means it has to have how many complex? Izzy? Has to have, which one? 1 or 2? Has to have 2, okay? Because it has to add the 3. It's a degree 3, right? Now, what happens if I shift this graph down? What changed? Do I have complex zeros? Alexander, you're saying no. I still have my 1 real zero right here. And what's going on with this 0 right here? Multiplicity, right? So you count that as 2. So there's 3 real zeros here, right? So some of the questions you have today will kind of force you to think about that. And it's more of a conceptual idea, less procedural, right? And so this was these 2 slides, the previous one and this one, they were part of your 2-3 notes. We kind of discussed quickly, and I said eventually we'll come back to them. So this scenario right here is just kind of reliving what we just talked about, and this is conceptual, right? So the first 2 graphs here are degree 3s, which means they have to have 3 zeros. They must, no matter what, have 1 real zero because it's an odd degree polynomial. And you can see it, they cross the x-axis here and here, right? So they both have 1 real zero, but because that's the only x-intercept, that means there's going to be 2 complex zeros, and you can kind of count 1 turn, 2 turns, complex zeros exist somewhere. That's the behavior. So if you have 1 real, then you have to have 2 complex, and that's a total of 3, right? Same with this one, it's just shifted below the x-axis, but you still have 1, and then there's, the concavity switches twice there without crossing the x-axis. We have complex zeros. They still total the 3. 1 real, 2 complex. The next 2 are degree 4 polynomials, which means you have to have 4 zeros, right? I have 2 real ones right here, but that's it, which means I have to have 2 complex zeros, right? And then lastly here, this is still degree 4. There are 0 real x-intercepts, or 0 real zeros, which means I have to have 4 complex zeros, right? And you can kind of count it, so let's get rid of the blue. So the first one is here, right? It changes twice. There's 2 turns right there without hitting the x-axis. Complex zeros exist from that behavior. And you got to use that middle turn, that second turn, when you count the second one. But there's a turn and another turn for the blue. There's another pair of complex zeros, okay? So you have 0 real zeros and 4 complex zeros there, which total to 4. What are your questions? Pretty good? Okay. That was just a review to help you process some of the conceptual ideas you're going to deal with today.